Good morning. It's Coach Primo again. Today's lesson, we're going to talk about limited growth, and we'll look at some examples like bacteria growth in an agar dish, and we'll look at the comparison of unmitigated or unrestricted growth of bacteria versus limited growth of bacteria. We'll also talk about the growth of maybe, bears in a habitat that's made specifically for them. But in the meantime, let's get started with our bell ringer. What happens when the variable in an explicit function is in the exponent? For example, y equals 2 to the x power. How does the range change when the domain changes? So when x moves by 1, what happens to y? Okay, sometimes that causes problems for people to understand. But exponential growth you should have gone over already since Algebra 1. And you probably went over a little bit in geometry and a lot in Algebra 2. So this should be something you should be very familiar with. Whenever, in this particular instance, 2 to the x power, when 2 is 0, the answer is 2. Y is 1, because any number raised to the 0 power is 1. 2 to the first power is 2, to the second power is 4, third power is 8, fourth power is 16, and so on. These are binary numbers. We went over binary numbers in the TCP unit, and it helps to understand this really well. It moves exponentially. So that's what happens to the range when the domain changes by 1. It changes by 2. Or by a multiple of a ratio of 2. We talked about common ratios, and that's what it is. All right, so what's making life great in your life? What's making life great in my life today? I leave for Galveston, taking some of my students that are in Mr. Torres's class and the culinary arts class down to Galveston for a regional competition, and hoping they do really well. I'm just an innocent bystander that happens to drive them down there. Anyway, that's what I'll be doing the next 2 days. It's your last lesson before next week. There'll be no assignment at the end of this. Good news, but you are responsible for the material that's inside it. So let's move on. Okay, so consider the exponential function we discussed in the bell ringer, y equals 2 to the x power. Let's fill in the table of values for the function. We'll find the rate of change between consecutive values in the function. That's delta y. Delta y stands for the change in y. And what pattern do you see for these delta y change? So let's start. When x is 0, 2 to the x is 1. When x is 1, 2 to the x is 2. The change in y is 1. When x is 2, y is 4, and the change in y is 2. Is that true? Yeah, 2 plus 2 is 4. When x is 3, y is 8, and the change in y is 4. And x is 4, y is 16, change in y is 8. X is 5, y is 32, change in y is 16. What do you notice about this value of y and this value, the change in y? Did you notice that both the value of y changes exponentially and the value of the change in y changes exponentially? That's by design. I'm pretty sure the person that created exponents decided that's how it was going to happen. No, actually, that just happens naturally. So, yes, our change in y, our change in exponents is actually exponential too. So, in Activity 3, we learned about a sometimes fatal antibiotic-resistant staph bacteria, methicillin-resistant Staphylococcus aureus, or MRSA, growing in an agar dish. And the initial area occupied by the bacteria in the agar dish is 2 square millimeters, and the increase in the area by 20% each week. The table below gives the area of the bacteria over several weeks. And we're going to use the table to describe the rate of growth of the area of bacteria, which is the change in A. Okay. So we went from 2 square millimeters to 2.4 square millimeters. That's change of 0.4 square millimeters. Next week, we changed by 0.48 square millimeters to 2.88. That's a common ratio of 1.2. We divide 2.88 by 2.4, and that gives us 1.2. And we can use our calculator here real quick. Let me clear that out. And 2.88 divided by 2.4 equals 1.2. And that's where we get that information from. Let's get back to where we were. We'll take just a moment. Fix this real quick. Okay. And as you can see, as we move on, that common ratio remains the same. All right. From the table, the rates of change are not constant, but instead they have a common ratio. This means the rate of change of the model is growing at an exponential rate. The common ratio is the same as the common ratio between the area and amounts. In other words, we can see that the exponential change in the area is the same exponential change in the change of the area. So, suppose a quantity increases at a rate proportional to the quantity, and the constant of proportionality is 0.2. If the initial quantity is 2, write a difference equation that describes the statement above and find several values of the quantity. Okay? So 2, the change in y is 0.2 times 2, or 0.4. So y is 2.4. The change in y is 0.48 from 2.4. We add that to 2.4, we get 2.88. We do that for several values, and we can see a pattern that begins to exist. The change in y is actually 0.2 times y. Well, we know that. It's right here in the process. Whatever y is, we multiply by 0.2 to find the change in y. We do that every single time. Y is 2.8, we multiply by 0.2. Y is 3.46, we multiply by 0.2. Find the change in y from 3 to 4. Okay? So we use a spreadsheet, and this is what we've done. This is actually change in y right here. Should be delta A, I'm sorry. We're going to generate about 75 values of the table. I'm only going to show the first 20 here. The spreadsheet allows us to use the recursive rule to generate the data. That's what we've done. Notice the unrestricted growth in this. The unrestricted growth here is growing immensely, very quickly. This is what we're adding to that to get to this. Wouldn't that stop the, what about if the bacteria is in an agar dish that's not very big, it has 100 square millimeters? Wouldn't that stop the growth of the bacteria? And it does. They're growing in only has an area of 1,000 square millimeters. The growth of the bacteria is limited in the lab by that size. The bacteria can still be modeled by a proportional difference equation, but now the rate of increase of the bacteria's area is directly proportional to the bacteria's area and the difference between the agar's dish area and the bacteria's area. This constant of proportionality is a ratio of the original constant of proportionality, 0.2, and that maximum area of bacteria that can reach 1,000 square millimeters. So now it can be written as follows. The change in the area over the change in time is 0.2 over 1,000 times the current area times the difference between the limit, 1,000 square millimeters, and the current area. So since we're moving in increments of 1 unit of time, we're going to use that 1 unit of time here in that difference equation. It'll simplify the work because we only want to see the change in the area over the course of 1 unit. We'll use that difference equation to find the new values of A, and we'll use a spreadsheet to calculate about 75 values. And that's what we've done. A portion of the table is shown. The equations are written in the second data row. And for A is restricted versus A unrestricted. And the results of the equation are filled in the rows below. So after only 10 units of time, the unrestricted is about 0.1 millimeters square larger than the restricted. We're already seeing some limits to it. We look carefully. What do we notice when we compare? First 15 weeks, the area is almost the same in the two growth models. But then the restricted growth slows down. You see it starts to slow right here. And we're looking at the last 15 values of the growth in restricted and unrestricted. Notice unrestricted is already in the 112,000. And by the time we're done, it's 1.7 million millimeters square. But we're already so restricted in the agar dish that it has nowhere to grow. So it slows down. And after 75 weeks, it's only at 999.89 square millimeters. So what that means is by the 75th week, the unrestricted growth model shows the area of bacteria 1.7 million square millimeters, while the restricted growth model has reached a limiting value of almost 1,000 square millimeters. We look at this curve created by the restricted growth, and there are some very unique features to this curve. This curve is called a logistical curve, okay? Not sure where this link goes to. I don't know. Let's see, restricted versus unrestricted growth. Let's back up. That's what it looks like once we've created. This is restricted versus time. Notice that it stops and peaks and it never makes it to 1,000. That's after 75 weeks. It's a pretty good graph to explain the situation. All right. Unrestricted bacteria growth models exponential growth and has a common ratio of 1.2. We're going to use a spreadsheet to find the ratio between successive values in the restricted growth model. What do you notice, and how does this support the graph in the last slide? All right. The ratio between successive values in the restricted growth data starts out close to 1.2, but it slowly decreases. And it decreases to a point by the time the graph's flattening out, it becomes constant around 0.8. It resembles the limiting nature of an exponential function along the x-axis. But now the limiting value is 1,000. Okay? What's the maximum sustainable number of black bears for this habitat? So let's look at the situation. The scenario is that a rancher has decided to dedicate a 400 square mile portion of the ranch as a black bear habitat. And he works with the state, and he plans to bring 10 young black bears to the habitat in an effort to grow the population. His research shows that the annual growth rate of black bears is about 0.8, and black bears thrive when the population density is no more than 1.5 black bears per square mile. So that density of the bears thriving is going to be a limiting factor. So as long as we have 1.5 black bears per square mile in that 400 square mile portion, we know exactly how many bears will fit in there. And so assuming a population density of 1.5 bears per square mile, the 400 square mile habitat can sustain 1.5 bears per square mile times 400 square miles. So that is 600 bears. It can sustain 600 bears that will thrive. After that, there'll be so much competition, we'll lose bears and we'll go back to 600 bears. So write a recursive rule showing the restricted growth in population for the black bears. Now, the constant of proportionality is a ratio of the unrestricted growth rate and the maximum sustainable population. So this is the recursive rule of restricted growth. The population of the bears in the next value equals the population of the current population of bears times the ratio of proportionality times the current population of bears times the maximum number of bears minus the current population of bears. Well, Pn is the population after n years, and M is the maximum population. Constant proportionality, R, is the ratio of the growth rate, the maximum population. So for this situation, the rule is P subscript n plus 1 is P subscript n plus the ratio of proportionality we've already discussed times the current proportion, or the current population, times the maximum population, 600, minus the current population. Now, where do we get this 0.001333? Well, let's see. Make a table and graph showing the yearly population. We start with 10, and every year we have growth. The first year we have almost 8 new bears. Then we have more new bears, a lot more new bears, and it gets to a point about 485, and all of a sudden it just plummets. The growth plummets because the limit of bears is preventing the bears from getting any more. There's so much competition, you can't have more than 600 bears. After that, they start to languish, and the population of bears goes down. So the population will reach 500 bears in the middle of the 9th year. Okay, see where it goes. We're looking at the number of years on the x-axis, and 500, which this green line describes. And the green line crosses that curve right at where the x-axis is at around 9 years. All right, I'm going to launch you with this. Bear hunting seasons in selected states. Why is that important? Because they don't have a fenced-in area to keep those bears limited. they have hunting that reduces the population of bears. If bear population were to explode, we would lose some of the sanctity of living in those states because the bears would be very intrusive and they'd have no problem coming into our houses and taking our lives. So bear population is important. In Maine, there's 30,000, so they take about 1/10 of those bears hunting. Even though they have 11,000 licenses they sell every year. So the land area of 35,000 square miles is hard to find a bear. Colorado is even harder because they sell a lot of licenses, but people are not really successful hunting bears there. They only get about 1,100. Pennsylvania, there's a lot more success hunting bears, a lot more licenses sold for bears, and that's partly part of the reasons they do. Look at the success rate, though. Colorado has a low success rate. Pennsylvania has a very low success rate. And Maine has a extremely high success rate. It has a lot to do with this right here, that out-of-state license. What's the point of this? If you don't have some way to limit the growth of bear population, you might want to have a hunting season to help limit it, because that'll take away some of the bears and it'll help stem the tide of the growth of bears. And unmitigated or unrestricted growth of bears would cause all kinds of problems. Okay, no lesson for this assignment. Be sure you understand the material. I expect you to watch this video all the way through. In the meantime, be blessed and be a blessing.